Now, today's topic is interpolation method for solving nonlinear programming problem. Now, interpolation methods are very useful methods and very efficient method for solving nonlinear optimization problem, and it is one of the very important line search technique for solving nonlinear. Now, there are various interpolation methods are available. One of that is the quadratic interpolation method, and other one is the cubic interpolation method. Now, what it does, whenever a function has been given to us, if the function is differentiable, then we can proceed further. Even if it is not differentiable, then also we can use the quadratic interpolation technique. What it does actually, I will start my lecture with the quadratic interpolation method. Now, the given function, for example, there is a function f x is equal to say x square e to the power x square plus x into e to the power minus x. Some range of x is given to us. Now, if I want to minimize this function, then the function will be differentiable if it is differentiable. Now, sometimes it happens that it is not differentiable. Now, we can just approximate this function with the quadratic polynomial, that is the idea. For example, if this is the function for us, graph of this function. Now, the function assumption must be there for applying the quadratic interpolation and the cubic interpolation method, that the function must be unimodal in the given range. Now, if this is the range for the function, then we can just approximate this function with a second degree polynomial, say parabola, all right, and with it. Now, if I just approximate with this quadratic function, it is very easy to handle the quadratic function. That is why we will go for the minimum of this quadratic function, and we will say that is the approximate solution of the given nonlinear programming problem. That is the idea for quadratic interpolation problem. That is why in general, let us consider we are having a function minimize f x, and the range for x is given as from a to b. As I said that I will approximate this function with a quadratic polynomial, say p x, then it is a second degree polynomial a 0 x plus a 1 x plus a 2 x square. Instead of minimizing f x, we will minimize p x, and we will check if x bar is the minimum value for this optimal solution, for this optimization problem, and if x star is the optimal solution for this polynomial, then we will do the iteration. We will first find out x star, we will check the condition whether x star is closer to x bar or not. If it is very closer, for mathematically we can say x star minus x bar lesser than epsilon, where epsilon is a very small pre-assigned value, all right. Now, if this says so, then we will minimize p x, and subject to the condition again x belongs to a b, we will go for the minimum value. And how to get the minimum? As we know, the necessary condition would be first order derivative of p with respect to x must be is equal to 0. That is why we get from the given polynomial, this is equal to a 1 plus a 2 x, and at optimal point at x star this must be is equal to 0. Thus, we get the condition that x bar must be is equal to minus a 1 by 2 a 2. This is the necessary condition for us. And what is the sufficient condition? That is p double dot x must be greater than 0, as we want to get the minimum of p x. If this is greater than equal to 0, certainly a 2 must be greater than 0. That is the condition for optimality of p x. Now, our task is to determine the values for A naught, A1 and A2, because these are the coefficient of the corresponding Px. Now, for finding out the values for A0, A1, A2, we need to have, since 3 unknowns are there, we need to have 3 equations for this case. Now, for getting 3 information, we can consider 3 points in the interval A to B, say x1, x2, x3, and we will say that fx is equal to px at these 3 points, then we will get 3 equations, and with 3 unknowns, the coefficients of the polynomial A0, A1 and A2, and we can solve it. Otherwise, we can have information in other way also. Functional value at 2 points, say x1 and x2, we know the fx value, we will equate fx with px at these 2 points, x1 and x2, and after that there is another information, that is the first order derivative of fx is given in one of these 2 points, that is why f dot x1 or f dot x2 is known to us. In this case also we are having 3 equations and we will have 3 unknowns, A naught, A1 and A2. That is why we can solve that polynomial, rather we will get that polynomial and we will check the minimum value of that polynomial close to the minimum value of fx or not. How to check, I will tell you in the next, but first I will just tell how to find out the value for A0, A1 and A2. As I said that functional value at these 3 points x1 is equal to px, that means it is equal to A0 plus A1 x1 square x1 plus A2 x2 square. There is another point in the given interval AB, that is x2. We have A0 plus A1 x2 plus A2 x2 square, this is x1. Fx3 is equal to A0 plus A1 x3 plus A2 x3 square. Now, we are having 3 equations and these are the functional values, these are constant for us. That is why solving these 3 equations we will get the coefficients A0, A1 and A2 like this. Just after some simplification we get A0 is equal to fx1, x2, x3 into x3 minus x2, fx plus fx2, x3, x1 into x1 minus x3 plus fx3, x1, x2, x2 minus x1 divided by x1 minus x2 into x2 minus x3 into x3 minus x1. And in this way we will get the values for A0, A1 and A2. Once we get the value for A0, A1 and A2, that means we are getting the corresponding second degree polynomial and we can construct Px. Now, we will go for the optimal value for this Px. Now, the optimal value for this Px, the basic condition is that x star, that the optimal value must be equal to minus A1 by 2A2, just I got it from the necessary condition. That is why we will just substitute the values for A1 and A2 what we got in the previous case here, and we will get the value for x star. And we will check in the next whether x star is the optimal value or not. If it is optimal, we will declare this is the approximate optimal value of fx. If it is not so, then we have to proceed further. That is why let me write down the algorithm for this, how to get the solution through the quadratic interpolation method when 3 points are given to us. Now, algorithm tells us that algorithm we can construct in this way, because just now I have gone through the process. The step 1 would be initialize x1 is equal to A1, x1 is equal to A, some given value, and x2 is equal to B, x3 is equal to B. I can take a middle value here, that is C, where C is in between A and B. That means we are having 3 points here, A, B and C. If C is not given to us, we can take the middle value of A and B. If C is given to us, then we will get C accordingly. Now, selection of C is very important, because if C is far from the optimal value, then we need to do more number of iterations. If the C is lightly selected, then we will get the optimality very quickly. We will move to the next step. We will calculate the value for x star as minus A1 by 2 A2, all right. And how I will get A1 and A2, I have just showed it to you. Now, step 3, we will check the condition whether x star is close to C or not. If it is close to C, that means the difference between x star and x2 is very small, that is epsilon, then we will stop, otherwise we will proceed to the next step, step 4. This is the interval for us. This is x1, this is x3, and the middle value is x2. Now, we are getting x star. X star can be this side of x2, x star can be this side of x2 as well. If x star is in the left hand side, that means we are considering case 1, that is x star is in the left part of x2, where fx star is lesser than fx2. Then what is happening? This is a process line search technique, that is why our initial interval of uncertainty is given x1 to x3. We are running the quadratic interpolation technique, and in each iteration the interval size will be reduced. That means, we will eliminate a portion of the interval in each step, so that we will get at the optimal step the interval size is very small, then only it is accepted to us. Now, x star is fx star is lesser than fx2. That means, it is very clear that the optimal value cannot lie from x2 to x3, as I assume that function is unimodal in the interval x1 to x3. If this is so, then we will eliminate x2 and x3, x2 to x3, and we will declare the new x1 as x1, new x2 as x star, and we will consider x3 as x2, all right. Then we will get another interval x1, x star, x3, that means we will get up to this, and we will run the, we will find out the x star value. If x star is closer to the middle value of that, not the middle value, middle point of that interval, then it is accepted, otherwise rejected. This is one of that case I have considered, that x star is in the left part of x2 and functional value of x star is lesser than fx2. If the other case arises that x star is lesser than x2, but fx star is greater than fx2. Since we are going for the minimization of functional value, that means that fx star value is higher than fx2 value. Function is coming in this way in that case. That means the minimum value cannot lie within this interval, that is x1 to x star, if I consider this as x star. Thus, what we will do? We will eliminate x1 to x star, and we will declare the new interval from x star to x3, considering x2 as the midpoint at the point in between. Clear? The other case may arise as well, that is x star is in the right hand side of x2, but fx star is lesser than fx2. That means function is x star is here now, and functional value of fx star is lesser than fx2. That means function is coming down in this way. Then we can eliminate Up to this there cannot lie any minimum value, because f x 2 value is higher than f x star value. That is why we will eliminate x 1 to x 2, because minimum cannot lie there, and we will again apply the technique, that is we will calculate with the new points a b c, we will calculate x star. We will check whether this is very close to the middle value of these interval x 1 to x 2 to, rather this is x 2 to x 3, and we will proceed. Case 4, once I will apply this technique for the problem, then it is much more clear to you. Now, if x star is greater than x 2, but f x star is greater than f x 2, it means that f x star value is higher than the f x 2 value. That means the function is coming in this way, in this case. Then the minimum cannot lie from x star to x 3. That is why we will just eliminate this interval in the next. All right. Minimum must lie from x 1 to x star in this case. Then again we will redefine a b c for each of the cases. Whenever whatever will occur, we will see the values for a b c, we will calculate x star, and we will check whether this is optimal or not. This is the quadratic interpolation technique, when in 3 points the functional values are given to us. All right. We can have another case as well for the quadratic programming problem, quadratic interpolation method, that is the method when only 2 points are given to us. Functional values at x 1 and x 2 given, and we have the first order derivative of the function, and the value at x 1 is also given to us. Then in this situation, how to apply quadratic interpolation technique, because the previous case it was that 3 point values are given, 3 points are given, here 2 points and one first order derivative of f. If it is given, again we will apply the same technique, we will approximate the function with a polynomial p x, and the p x would be equal to a 0 plus a 1 x plus a 2 x square. We need to find out the coefficients of a 0, a 1 and a 2, so that we can approximate the polynomial, we can approximate the function f x with the polynomial p x. Now, when these are given to us, then we can have 3 equations like this. F x 1 is equal to a 1, a 0 plus a 1 x 1 plus a 2 x 1 square. We are having f x 2, f x 2 is equal to a 0 plus a 1 x 2 plus a 2 x 2 square. We are having the functional value x 1, f prime x 1. Certainly, this is equal to a 1 plus 2 a 2 x 1. 3 equations, again 3 unknowns for us. We need to find out the values for a 0, a 1 and a 2 with these 3 equations 1, 2 and 3. Just I give you some simplified value. How to proceed for that? Let us go for 1 minus 2. Then we are getting f x 1 minus f x 2 is equal to a 1 into x 1 minus x 2 plus a 2 into x 1 square minus x 2 square. Now, we will substitute the value in the third equation. Then what we get in the third equation, from the third equation we will substitute the value for a 1. Then we will get f x 1 minus f x 2 is equal to, in place of a 1 we will replace f prime x 1 minus 2 a 2 x 1, and the rest thing I will just keep as it is. then this is the equation with only one unknown A2. From here we will get the value for A2 as fx1 minus fx2 minus f prime x1 minus x2 divided by minus x1 minus x2 square. Now, we can have A1 as well. By substituting the value for A2, we will get A1 as f prime x1 plus 2 fx1 minus fx2 minus f prime x1 minus x2 divided by x1 minus x2 whole square and here x1. Once we are getting A1 and A2, we may not calculate A0 because as we have seen from the necessary condition that p prime x must be is equal to 0 and it gives me the stationary point x star as optimal value and this is equal to minus A1 by 2 A2. That is why for calculation of the optimal value we may not calculate A0. With these two values we can proceed to the next, that is x star is equal to minus A1 by 2 A2 and this gives me the value as x1 plus half f prime x1 minus x2 square divided by 2 fx1 minus fx2 minus f prime x1 into x1 minus x2. This is the value for the optimal point. Now, we can develop the iteration process with this from this equation by substituting x star as the next approximation when xk and xk minus 1 values are given to us, and this can be written as, and by substituting this as xk and xk minus 1 we will get xk plus half f prime xk minus xk minus 1 square divided by 2 fxk minus fxk minus 1 minus f prime xk minus xk minus 1. This is the iteration formula for us. That is why when xk and xk minus 1 is given, both the values are given to us, we will calculate the value for xk plus 1 and we will go for the check whether the convergence of the sequence of values is there or not. For checking the convergence there are few processes. First thing is that if x star is the optimal value for us, it could be minimum, it could be maximum, then at this point the function also has the optimum, the minimum or maximum value. That is why I can say that f prime x star is very small, closer to 0. I cannot say this is equal to 0 because I am approximating fx with a polynomial px. That is why it may not happen that this is the exact minimum for fx. That is why we can check whether f prime x is lesser than epsilon or not. If it is lesser than a very pre-assigned small value, then we can accept x star as the optimal solution. There is another check also there, this is available in the literature. We can also go for the fx star minus px star divided by fx star. If this value is lesser than epsilon, that also could be a check. And other check, as I said, that if the interval, that is xk and xk minus 1, this interval is very small, then also we can stop our iteration process. These are the all alternative processes for checking the convergence of the sequence of values of xk plus 1, and rather that will lead us to the optimal solution for the given function fx. Now, let me apply this one for a problem given like this example, where we need to minimize f x is equal to e x square plus 2 x square e to the power minus x, and the interval has been given that x is in between minus 1 to 1. As we see, the function involves a exponential function. We can go for the other techniques as well for getting the optimal solution, but if we apply the quadratic interpolation technique, it has been seen that quadratic interpolation technique is much more efficient than the Fibonacci golden search technique, as I discussed before, and thus quadratic interpolation method convergence is very quick, very faster than other methods. Then we can apply the quadratic, and I will discuss in the next the cubic interpolation, and we will see cubic interpolation technique is much more efficient than other line search techniques like Fibonacci, golden section and others, and the quadratic interpolation technique as well. Now, if we apply the quadratic interpolation technique, then as we see in the first iteration, we are having the value as x 1 as minus 1, x 3 is equal to 1, and as I said, if 3 points are not given to us, if no other information is given, then we can consider the middle value as x 2 point. That is why we are having x 1 minus 1, x 2 equal to 0 and x 3 is equal to 1. Then we can calculate the values for A0, A1 and A2. To construct Px. See how to get these values, as I just showed you. We will calculate A0, A1 and A2 with this formula, because we know x1, we know x2, we know fx1, fx2, fx3 as well. We will just substitute the values here and we will get A0, A1 and A2. From there we will calculate x star. This is equal to minus A1 by 2 A2 with the formula I have showed. Now, this value will be 2.244607. That means, in this iteration we are getting the minimum point of the given polynomial Px with these A0, A1, A2 values is x star, and we can declare this is the approximate value of the minimum value of the function, but we need to check whether this is correct or not. That is why we will go for the functional value for fx at x star. We see the functional value is 1.155358, and we will check. If I just check the condition, as I said, I can check the first order derivative of function at point x star. If it is very small, then we can stop our iteration, or other check, as I said, we will just check the value, the difference between x star and x2. We see the difference is 0.244, that is very high, we cannot stop, but we can check other way as well, as I was discussing, that is this is the value, and this value is coming as 0.38. This is also quite high. That is why we should not stop here. We cannot declare x star, though this is the minimum value of the polynomial Px, but we cannot declare x star as the minimum value for fx, that is e to the power x square plus 2x square e to the power minus x. We will proceed to the next. How I will proceed to the next iteration? Iteration 2, that means the interval we are having minus 1, 0 and minus 1 and 1, this interval will be reduced in the next iteration, and this will be reduced according to the unimodality property. As I said, function is unimodal in the given interval. That is why we will check the functional value at minus 1, functional value at 0, functional value at 1 and also functional value at this point. And we see the functional value at 1 will be higher than the functional value of x star. That means minimum cannot lie within that, and functional value is decreasing. Again, that is why we will consider the next interval as x1 is equal to minus 1, x2 is equal to 0, no 0.24, x2 equal to 0 and x3 is equal to 0.244607. That means, we are discarding 0.24421, because with unimodality property we can check the minimum cannot lie here. Again we will go for the calculation for A0, A1 and A2 and we will get x star as well here. X star will come as in this situation 0.04, no sorry, this is 0.071566 and we will check the functional value at this point as well. We will see the functional value is 1.0146 and we will see this functional value is very close to the functional value at 0, functional value at 0 is 1, it is very close. That is why we can either go for the check, as I said, the first order derivative of f at point x star, we will see the value will be very less, and otherwise we can calculate this value as well, f x star minus p x star divided by f x star, and this value is coming as 0.04. This can be considered as a very small value. If we are happy with this value, we can stop our iteration and we can declare that this is the optimal solution for the approximate optimal solution for the given function. But if we are not happy with this value, we can proceed in the next again. How? Again we will just reduce the interval from -1 to this point with the unimodality property, and accordingly we can proceed in the next, and we will see that we will get better minimum, better x star. As many iterations we will do, we will get better iterations further, but at some point it will converge. There we need to stop at least. Since I am doing it manually, I am stopping here with the acceptance that this value is acceptable to me. Now, this is the way we can use the quadratic interpolation method for solving any function given, and a function can be complicated in nature also, then also we can apply the technique very well. That is all about the quadratic interpolation method. Let me go to the next, that is the cubic interpolation technique. That is the extension of the quadratic interpolation technique, but cubic interpolation method is popular and much more better method than other line search technique, but one disadvantage of this method is that the calculation is very long, because as you see we are going for the cubic interpolation method. That means, we are, instead of approximating the function with a second degree polynomial, we will approximate the function with the third degree polynomial, that is cubic function. And since this is a third degree polynomial, instead of having in the quadratic we had the 3 unknowns, here we are having 4 unknowns. That is why the information, we need 4 information to calculate the value. Let me go to the process further. The cubic interpolation technique. We are having the function minimize f x, x belongs to a b. We are approximating the function f x with a polynomial p x, and this polynomial is of third degree polynomial. Now, for doing that we are having 4 unknowns, that is why we need 4 equations. How to get 4 equations? Either the functional values at 4 points should be given to us, and we will equate that functional value of and the functional value of the polynomial, we will equate both together. That is, either we will calculate f x I is equal to p x I for I is equal to 1 to 4, and we can get the values for a0, a1, a2 and a3. Otherwise, we can have functional values at 2 points and derivative value at 2 points and the same 2 points. That means, we will have 4 equations again, and we are having 4 unknowns, that also quite possible. And otherwise, we can have the 3 points are given and 1 derivative value also given, it could happen also. There also we will have 4 equations and 4 unknowns, and we can solve it. Now, I will just consider one case because other case calculations are almost similar to this case. That is why we will consider the case where 2 points are given. That means we are having fx1, fx2, and we have the derivative of f at x1, we have a derivative of x2 at x2. All right. These are all given to us, and with this information we will proceed to approximate the polynomial. We can consider the polynomial in this way: a0 plus a1 into x minus x1 in different just little deviation I have taken from the quadratic interpolation technique. Again we can just approximate this polynomial as a0 plus a1 x plus a2 x square plus a3 x cube, that also quite possible, but here I am taking another way so that I will get a nice and quick result from here, cube, in such a way that Px1 is equal to Fx1, Px2 is equal to Fx2, P prime x1 is equal to F prime x1 and P prime x2 is equal to F prime x2. Then we will have 4 equations and 4 unknowns. Then from this information what we get, that A0 must be is equal to Fx1, all right. From the second, P prime x1 equal to F prime x1, P prime x1 means A0 plus A1 x1, all right. No, sorry, A0, no, only A1, because P prime x is equal to A1 plus 2 A2 x minus x1 plus 3 A3 x minus x1 square. That is why from here we are getting at point x1, if P prime x1 equal to F prime x1, then we are getting A1 is equal to F prime x1, all right. Now, what about Px2? Px2 gives me the Px2 equal to Fx2 gives me the equation Fx2 is equal to A0 plus A1 x2 minus x1 plus A2 x2 minus x1 square plus A3 x2 minus x1 cube. Here you see where we know the value for A0, we know the value for A1, that is why this will be equation with only 2 unknowns A2 and A3, because x1, x2, fx2 everything is given. A0, A1 can be calculated very easily from the functional values at x1 and derivative value of that function at x1. And from the other condition, that is P prime x2 is equal to F prime x2, from here we will get this value. F prime x2 is given to us, that is why we will equate this with A1 plus 2 A2 x2 minus x1 plus 3 A3 x2 minus x1 square. And with these 4 equations and 4 unknowns, we can get the solution very easily. And A0 and A1, A2, and these are the equations with A2 and A3 only. That is why again we will declare the necessary condition for getting optimal is P x star is equal to 0. Not only that, P double prime x star must be for minimization greater than 0. And if we equate P prime x star is equal to 0, we get the value for x star as that means A1 plus 2 A2 x star minus x1 plus 3 A3 x star minus x1 square is equal to 0. This is the equation for us. From here we get the value for x star as x1 plus minus A1 plus minus root over A2 square minus 3 A1 A3 divided by 3 A3. Okay. Because this is the equation of degree 2, we can use this and we will get the value for x star. And we are having another condition as well, p prime x star is greater than 0. That means we are getting that 2a2 plus 6a3 x star minus x1 greater than 0. This is another condition is given for minimum. This is the sufficient condition. Now, when a3 is equal to 0, here we get the value for x star as x1 minus a1 by 2a2. When C3 when a3 not equal to 0 and we are getting a3 equal to 0. Thus, if we calculate the values for a1, a2 and a3 from the given conditions as I showed before, then we will get the value for x star is equal to this, either this or that. Instead of considering both together, we can just simplify the case and we can declare by multiplying both sides, the numerator and denominator with certain value, we will get x1 plus a1 divided by a2 plus a2 square minus 3 a1 a3, and this can be considered a general equation. You see, we have considered only the positive values, positive value of x star. Why? Because sufficient condition tells us that if we consider negative value, then it will not satisfy. Thus, we will only consider the plus value here, and we are multiplying numerator and denominator with a1 plus this and we will get the solution for the given equation. Now, if this is so, you see there is a nice fact here. If we consider this function, even a3 is equal to 0, it leads to this value, that is x1 minus a1 by a2. This is the value. Here it should be a2, not a1. All right. Now, this is the way we can calculate the optimal value for the cubic interpolation, and the same procedure, if we are satisfied, then we can proceed to the, we will proceed, if we are not satisfied, we will proceed to the next iteration after checking the convergence. Convergence checking is again the same, that we will check whether fx star value is small or not. Either we can go for this, or we can calculate fx star minus px star divided by fx star, whether this is lesser than a very small value or not, and we can proceed further in this way. Let me take one example for this. The problem is minimize fx. We are having another polynomial of degree 5, and initial interval of uncertainty has been given that from 0 to 3. And the cubic interpolation technique we will apply means we will approximate this 5th degree polynomial with a lesser order polynomial, that is degree 3. Thus, we will approximate px with fx with px as a0 plus a1 into x minus x1 plus a2 x minus x2 square plus a3 x minus x3 square. Now, for this we are having information regarding, we know only x1 equal to 0, x2 equal to 3, we can have f prime x1 value, that would be is equal to minus 20, and f prime x2 value, that would be is equal to 250, all right. Then the function looks like this, and we have assumed that function is unimodal. This is x, this is f x. That means function is coming zero, it is negative, and negative to positive it goes in this way, all right, and minimum may lie, it could be this way as well, all right. If this is so, then we will calculate the values one after another. How? We will go for P0 is equal to F0. P0 equal to F0 gives me the value for A0 is equal to 5. P prime 0 is equal to F prime 0. This gives me the value for A1 is equal to minus 20. P3 is equal to F3. This gives the equation 9 A2 plus 27 A3 is equal to 108 by substituting the value of A0 and A1, and we are having another equation P prime 3 is equal to F prime 3. Then it will give me another equation 6 A2 plus 27 A3 is equal to 247, all right. Now, we are having two equations and two unknowns, and from here we will get the values for A0 as 5, A1 as minus 20, A2 as minus 46.33 and A3 is equal to 19.44, and we will calculate x star here. X1 minus A1 divided by A2 plus root over A2 square minus 3 A1 A3, and this value is coming as 1.83, and if this is the value, and we will go for the functional value, and we will see that functional value is not, that is the first order derivative of the function is not small enough, that is why we will go to the next iteration. How to get the next iteration? As we see that functional value is at 1.83, functional value is less, that is why the next interval we will consider as 1.83 and x2 is equal to 3, and we will calculate the, again we will go for f prime x1 and f prime x2, and we can calculate x star from here, and if this optimal solution is acceptable, then it is accepted, otherwise we will go to the next iteration further for getting the solution of the problem. And this is the way we can solve the quadratic interpolation, the minimization or maximization of any nonlinear function with quadratic interpolation or with cubic interpolation technique. Thank you for today.